In a radio frequency linear amplifier, the primary role of a low pass filter is to ensure that the signal being transmitted is clean by suppressing unwanted frequencies while allowing the desired signal to pass through unimpeded. Even though an amplifier is called linear, no physical device is perfectly linear. The process of amplification inevitably generates distortion products, specifically harmonics. The most critical role of a low-pass filter is to remove harmonics. Harmonics are multiples of your fundamental intended frequency. For example, if you are transmitting at 14 MHz, your amplifier will naturally produce smaller signals at 28 MHz, which is the second harmonic, or 42 MHz, which is the third harmonic, and so on. Without an LPF, these harmonics would be sent to your antenna and broadcast into the air. This causes interference with other radio services like aircraft navigation, emergency services, or TV broadcasts, which is both poor practice and illegal under radio regulations. LPF is designed with a cutoff frequency just above your highest intended operating frequency. It lets the 14 MHz signal through but acts like a wall for the 28 MHz and 42 MHz signals. By removing those harmonics, the LPF ensures the output meets spectral purity standards. Amateur and commercial radio equipment must limit spurious emissions, often called as PERS, or unwanted signals, to very low levels, often minus 43 decibels or better. It prevents your signal from bleeding into other bands, which is especially important in high power setups where even a small percentage of harmonic energy can be strong enough to disrupt distant receivers. In some designs, the LPF also plays a secondary role in system stability. While a standard LPF reflects harmonic energy back towards the amplifier, which can sometimes cause heating, specialized harmonic absorbing filters dissipate this energy as heat. They shunt harmonic energy typically into high wattage 50 ohm resistors. This protects the sensitive output transistors from excessive voltage or current spikes caused by these unwanted frequencies. Often, the output stage of an RF amplifier is combined with the LPF in a way that helps transform the low impedance of the transistors, often just a few ohms, to the standard 50 ohm impedance of the antenna system. In a more physical sense, if you were to look at the signal on an oscilloscope before the filter, it might look slightly jagged or distorted because of the added harmonics. After passing through the LPF, the signal becomes a smooth, clean wave. To summarize the features of an LPF, passband allows the fundamental signal to reach the antenna with minimal loss. Stopband aggressively attenuates frequencies above the cutoff, mainly harmonics. Purity ensures the transmitter only broadcasts on the intended frequency. Safety prevents interference with other critical radio spectrum users.